Hey YouTube, lately I got inspired by an interview I heard about a guy who had psychedelic experiences, and he was talking about consciousness and the brain and the universe and all that good stuff, and it inspired me to make the effect that you see behind me here. If you're interested in knowing how I made this and you want to make it yourself, then stick around. Alright, so this tutorial will consist of 2 videos because otherwise it will be too long. In the first video we will make the effect that you see behind me. So let's get started. Before I start, actually, let's see what this is made of. So basically what I did here is I overlaid a grid on top of the screen, kind of like so. And then for each grid cell, and I'm only showing 9 here, but there's a lot more over here. For each grid cell, I generate a random point somewhere inside of the cell, and then I draw a line from each cell, from each point to the point in each of the adjacent cells. So let's just first try to make that. All right. So I'm going to go over here, and I'm going to click New, Leave. All right, so the first thing I'm going to do is I'm going to do some housekeeping here. If you don't know what I'm doing, or if you're just starting with ShaderToy, I really recommend that you check out this video first. But if you're still here, then let's get started. So first thing I'm going to do is I'm going to make a black screen, and I'm going to make my UV coordinates so that they have the origin in the middle. Resolution.xy. And then they're also aspect ratio corrected. All right, so that just gives you a black screen. And now I'm going to define my smooth step as S, A, B, T. Smooth step, A, B, T. And that just makes it so I don't have to write smooth step each time. I could just write S. And now what we need is, let's start with a line drawing function, because obviously we're going to be drawing a lot of lines. So for that, I'm going to make a function that returns me the distance to a line. And that's going to take as an input a point to which from which we want to get the distance. And then it's actually the distance to a line segment. And a line segment has a start point and an end point, A and B in this case. And I'm just going to go through this a little bit faster. I explained this in other videos, but let's just go through this. So PA equals, so this is a vector from, it's P minus A, and vec to BA equals B minus A, and I'm going to make float T equals clamp. And I'm going to have to clamp this T value because I want the line segment, not just a line. And I'm going to do dot PA, BA divided by dot BA, BA. Basically what this does is it projects the PA vector onto the BA vector, and then it scales the output so that it is in the 0, 1 range. And then I have to also clamp that to 0 and 1. Because we want the distance to a line segment and not to a line, it's to an infinite line. And then I can return the distance, and the distance is PA minus BA times T. And let's just test that, make sure that I didn't make a mistake. So float M equals, float D, because I'm getting a distance, dist line. And as point P, I'm going to use my UV coordinate, and then for my 2 test points, I'm just going to use 0, 0, and 1, 1. All right, and that's just the distance to the line. That's not a line itself. I have to cut out a line, so I'm going to do that with a smooth step function, and this will can make different, like varying widths or line widths. So let me see here. Okay, so there we have a line drawing function. All right, the next thing we need is, because we're putting points in random positions, right? Like over here, these points are randomly positioned inside of each grid cell. We need a function that can return a random number. And we did it before with the sine wave, but I'm going to do it slightly different this time, because the sine wave solution, while it is the easiest and the fastest, it is not consistent across different systems. So if you look at it on a different machine, it will sometimes look a little bit screwy. So I'm going to do this a little bit different this time. So I'm going to start by taking my point and multiplying it by some larger number. So now it's multiplied by a larger number. Now I take the fractional component of that. So that now the p here is between 0 and 1. And now I'm going to do some screwing around with math in order to make it look more random. So I'm going to add the dot product of this vector p with itself plus some other number. And then I'm going to return the fractional value of p dot x times p dot y. This is just another way to get a random number. So let's check if that is correct. So I'm going to do m, and I'm going to use my UV coordinate as an input and c. And that gives me a random, for each pixel, it's going to give me a random output between 0 and 1. Now, I also want, so this is one that takes two numbers as an input, right? A vector 2 as an input, and it returns a float, so that's why it's 2, 1. I also want one that returns me two random numbers as an output, because if you want, like, say, a random position, well, that's a random x and a random y. So I'm going to also write that. And you could do something fancy here. But I'm just going to use this n21 function that I just made to do this. So if you thought about this a bit more, you could probably come up with something that is more efficient than calling n21 two times, but I'm more interested in keeping it simple. So plus n. So basically what I'm doing here is I'm just getting the x component, and then the x component will just go out like that. And then for the y component, I just add the x component, the random value that I calculated for the x, and added it, and then stick it in this function again. So let's see what that does. So n22, and this is returning a vector 2. So now we have to select whether we want an x or a y. So for the x, it shouldn't change anything because the x is just the original n21p here. But for the y, it should change. So let's see here. So the y, it changed. You have to check again. It looks good in full screen. Sometimes, because it's kind of dependent on these numbers. If you change these numbers, sometimes you get something that doesn't look random, that has kind of streaks in it or whatnot. And in that case, you have to kind of screw around with the numbers a little bit until you have something that looks random. All right, so now that we have that, so like now let's make the grid here, right? So for that, let's go over here. Let's multiply our UV by some larger number, and then I'm going to make a vec2 GV for grid UV, and that's going to take the fractional component of my UV. And let's just visualize that so we know what we're looking at. Let's do that down here. I'm gonna say the, well actually, let's set this to 0 over there, so that's black. And I'm gonna take the red and the green channel, and I'm gonna visualize my UV coordinates, my GV coordinates I just made. So now you see that makes a bunch of little boxes. Let's make them a little bit bigger. But these boxes have 0, 0 on the bottom left, and I don't want that. I want the 0, 0 in the middle. Well, that's simple enough. I just subtract 0.5 from it, right? Because it goes from 0 to 1, right? And 0 to 1. So if I subtract 0.5, well, then it will just go from minus 0.5 to 0.5. So let's see what that does. And so now my 0, 0 is in the middle. Great. Now, before I go any further, let's draw some outlines on these boxes, because if we do something else and we don't have this visualized, we can't see the grid anymore. I want to, just for debugging purposes, I want to be able to see the grid. So for that, I'm just going to say if gv.x is larger than 0.48 or gv.y is larger than 0.48, then show a nice red color. All right, because my grid cell, after I subtracted 0.5, right, it goes from minus 0.5 to 0.5, and so what this does is it just says for every pixel where my GV coordinate is very close to the edge, just draw it red, and the same thing for the Y, and that's how we get this grid here. So now, if we want a random position inside of each grid cell, well, then we need to first generate a like a random value for each grid cell, right? And that random value should be random, but for each pixel inside of the grid cell, it should be the same, right? So we can't use that noise that we just saw, because that was different for every pixel. We just want it to be different inside of each grid cell. And for that, first we need an ID for each grid cell. So let's make an ID value. So ID, and my ID is just going to be the floor of the UV coordinate. And fract and floor, I said it before, they're kind of two sides of the same coin, where fract returns the fractional component of a number, and floor returns the integer component of a number. So for like 45.3, fract would be 0.3 and floor would be 45. So this, while this GV now will go from well, it will repeat, right? Like, so it would go from minus 0.5 to 0.5, minus 5.5, and so on and so forth. The ID value will be 0 in the middle, and then 1, 2, 3, 4. And so we can visualize this as well. So if I go over here and I just look at the ID, you can see it's 0 over here, and then 1, 2, 3, 4, 5. And you can't see anything here because it gets too bright. So if I want to visualize that, I would have to multiply this by some smaller number to kind of see that each grid cell now has a different value. And over here they also have different values, it's just that they're negative, so you can't see what's going on over there. All right, so now we have the ID value, and now we can use that ID value to generate a dot at a certain position. So what I'm going to do is vec2 p equals some random position, right? So I can use my n22 function for that. I'm going to put my ID into it, and that gives me a random position, or a random number between 0 and 1, but I don't want it between 0 and 1. I have to get it in the same, I have to get it from minus 0.5 to 0.5. And now I can draw, let's say, a dot. So I can do this. First I have to calculate the distance from my current UV to my random point, and then I can use that to cut out a dot. I can just use this over here. So let me just take that, put it over here, and then put a semicolon, M. Let's see. I already defined D somewhere. So where did I define D? Oh, for my distance to my line. Okay, yeah, so dot we don't need anymore. Okay, so now we have a random point everywhere. But I'm going to do this slightly different. So because we also want to animate it, and so let's first animate a point. So for that, I'm going to actually, so let's just put this in its own function over here, this thing. So I'm gonna make a function called getPause, and it's gonna take as an input that ID. And then I'm going to go over here. I'm going to do vec2 getPause, and that just returns me the position of a point in a particular grid cell. And for now, let's just make that a rotating, an orbiting point, let's say. So for my x, I'm going to take the sine of I time, because I'm going to use I time because I'm going to animate stuff. So y equals the cosine of I time. And then I can return just that. Let's just see what that does first, x comma y. And my sine and cosine go from 1 to -1, which would be outside of the box, right? I have to scale that so that they're close enough so you can actually see. So if I do times 0.5, so now you see we have an orbiting point. But it goes a little bit too far because it goes all the way to the edge, and then it starts drawing this the center of the dot over there. So I have to multiply this by some smaller number here to kind of push it inside. But now we want a different position for each of these, and what we can do for that is like watch what happens if I multiply, let's say, only the x by 2. So now my sine in the x direction goes 2 times as fast as my cosine in the y direction, and watch what happens. So now I have a totally different shape, right? Now it goes into like an 8, figure 8. And if I if I change this even more, then it is going to do something different. So what I can do to get totally random positions and random motions in each of these grid cells is just to multiply this by 2 random numbers. So let's do that. So first I'm going to make a vec2n for noise, and it's going to take 2 inputs and it's going to give me 2 outputs here. So I'm going to throw my ID into it, and then here I can do times n dot x, and here times n dot y. And that just scales my time value between 0 and 1. So let's see what that does. So now you can see we have nice, as if by magic, like nice moving dots that are all moving in different directions at different speeds and whatnot. Now this can be made a little bit more concise, because we don't actually have to do this for the x and the y. I just did that to illustrate like how this is done, but we can actually do this in one go here. So we can do the sine of n, and if I just multiply this n by I time over here, then that should be the same thing. So let's see here. Yeah, so that does the same thing. Nice and concise. All right. All right, so now that we have that, let's start drawing some lines. Actually, no, before we draw the lines, we have to, so now we're at this point, basically. We want to get to this point. So for this point, what I'm going to do is for each grid cell, I'm going to go through all of the neighbors, and I'm going to note down all the positions of each of the cells, because and then once I have all the positions, then I can start drawing lines. So let's go over here. Let me just get rid of this guy. So I'm gonna make 2 loops, one for the x and one for the y. That's gonna loop through this. So the x is gonna loop from -1 to 0 to 1, and the y is gonna loop from -1 to 0 to 1. Which is basically the offset from the cell that we're currently at. So yeah, so let me go over, let's say go over here. I'm going to do for float y equals, I'm going to initialize it at -1, and then y is smaller than or equals 1, and then y plus plus. And what that will do is it will initialize that my float y to -1. So the first time it gets through the loop, y equals -1. The second time it will add 1, so the second time it will be 0. And the third time it will be 1. And the fourth time it will kick out of the loop, because then this condition will be false. So I'm going to do that for y, and then inside of that loop I'm going to do the same thing for x. So x there, x, and x. All right, and then inside of here, I'm gonna have to store a position of the cell, right? So, and for those positions, let's get rid of this guy over here. I have to get rid of this as well and get rid of this. Actually, let's just do that. Okay, and then over here, I'm gonna make an array of vector 2. So that's how you write down an array. An array is basically a list of 9 vector 2s. And then inside of here, I'm gonna have to go and add and calculate the position for each grid cell. So get pos, blah blah blah. We get to that. Before we do that, we need to have the index here. So what I'm going to do is I'm going to set the index I to 0 over here, and then each time we get through here, we have to add 1 to the index. You can do it like this, but a faster way is just to put the plus plus inside of here. That does the same thing. Okay. And then what we have to do inside of here, we have to have, okay, we get the pos for the ID, but the ID plus an offset, right? Because the ID cell is the cell that we're currently in, but we want to get the position for other cells, right? So it's the ID -1 for instance. Okay, so for that we're gonna have to make an offset, and actually I'm gonna add that offset here as a separate parameter. So I'm going to add vec2, and my offset is x comma y, right? So and I'm going to add that over here, my offset, vector2 offset. And so what do I need to do for this? Well, first my ID value here, so I need to like when I calculate my random position, it needs to be the ID plus the offset that I calculate that from, so plus the offset. All right, but now this thing calculates the local position. So over here I also have to add the offset because I need the position. Like I'm not interested in the of this grid cell. Let's say I'm not interested in the local position of this. I'm interested in the position with regards to relative to this cell, right? So that's why I also have to add the offset again over here. So that should give me the right position. Let me just compile, see where we're at. Okay, so we're not drawing any dots anymore. That's fine. So now that we have all these positions, now we can go through that list that we just made of positions. So it goes from 1 to 9, right? And now inside of here we can draw a line. So and these lines, they go from let's see here. Oh, okay, I don't have it here anymore. Frustrating. Okay, so basically these grid cells are they go from 0, 1, 2, 3, 4, 5, 6, 7, 8. Okay, so so the middle one, the middle one is the 4th, right? Because it starts at 0 and it ends at 8, so the middle one is 4. Okay. So what we're going to do here is each time we get through here, we're drawing a line from the middle one, so with my GV, from the middle one, so from 4 to the point that we're currently at. Okay, so let's see here. Okay, and we need to obviously make a line function because we only had a line distance function over here. Right, so I'm going to make a line function that will actually draw a line. So I'm going to vec2p, vec2a, vec2b, and then the first thing I need to do is get the distance to the line. So this line a p, a, b, and then after that I need to cut out a certain thickness of line, right? So I'm going to do 0.03, 0.01, d, and then let's just return that m value. All right, now we have a bunch of lines, so that's already getting somewhere. So let's have a look at that full screen here. So from each grid cell, it draws to the center of each other grid cell, right? There's just one problem, which is that sometimes there's a gap between, like say between here and here, there's a gap like over here. And that is because if we go over here, basically each cell right now is drawing a line from itself to its neighboring cell. But there could also be lines that cross this cell that don't start and don't end in this cell, right? Like in this case over here, this green line here. So we need to consider lines that go from this cell to this cell, from this cell to this cell, and from here to here, and from here to here, so that we catch them if they happen to overlap this cell. So we have to draw 4 more lines in order for this to work. All right, so after my loop over here, I'm going to have to draw 4 more lines. Okay, and the lines I'm going to have to draw is from position, okay, this is 0, right? This is 1. So from position 1 to position 3, right? So from 1 to 3 would be one line. From 1 to 5 would be another line. So let's put those in. So from 1 to 3, from 1 to 3, and then from 1 to 5. Okay, and you can see that already added a few lines, and now I need 2 more. Which is from okay, so this is 1, this is 3, and this is 5, this is 7. So from 5 to 7, and from 7 to 3, 5 to 7 and 7 to 3. So 7 to 3 and 7 to 5. So that should be it. All right, so let's get rid of this here. All right, well, we got something now. Awesome. All right, so the next thing would be to, I'm going to fade these lines based on their length, because we don't want all lines to show. We only want them to show when 2 points are close together. And so for that, I'm going to go inside of my line drawing function, and I'm going to multiply my line by some number that is 0 when they're too far, when these 2 points are too far from each other. So we'll just write it out and then I'll explain. Length A minus B. So length A minus B is the distance, or is basically the length of the line segment. And here I'm saying, okay, if the length of the line segment is larger than 1.2, then don't draw the line, or multiply it by 0, so it becomes invisible. Between 1.2 and 0.8, it slowly fades in, and after 0.8, it is fully visible. So let's see what that does. And look at that. And you can tweak these values. Like I said many times before, making shaders has a lot to do with, sitting there with a cup of tea and tweaking values for a long time until you have something. But I'll leave that up to you. All right, so now the last thing would be to actually draw a little sparkle, if you will, on each of these points. So for that, I'm going to go inside of this loop here where we draw all the lines, and we're going to add some sparkle. So I'm going to do float sparkle, and you might think, oh, we can use a smooth step for that, and you could, because we've used smooth step before to draw like circles and whatnot. But in this case, if you want a sparkle, if you want anything that looks like it's a light, then the smooth step doesn't work very well, because the fall off of the smooth step, it goes to 0 very quickly, and that stays at 0. Whereas if you want something that looks more like a light, the fall off will go close to 0 very quickly, but then it's kind of like an asymptote. It never gets to 0. So even if you're far from the light, there's still a tiny contribution to that light. And so to do that, let's first get let's make a vector that goes from the point that we're looking at, which is point PI, to the current, I forgot on equals, to the current pixel that we're at, which is GV. Okay, so that's our vector, and then instead of a smooth step, I'm going to do 1 divided by the length of that vector. So the length of J. And let's just add that and see what happens. And I will probably get all white, but we can tweak that. So let's see here. Yeah, so that goes all white. But if I multiply this here, so I make that vector longer. Yeah, so like now you can see that it, and you can see this looks much more like an actual light. The only problem is because this fall off doesn't go to 0 fast enough. You can see, well, first of all, it looks a bit too foggy, right? And second, you can start seeing the edges of the cell, or you can see the cell boundaries, like because the fall off is too slow. And so what I can do here is make that fall off faster by squaring it. So instead of 1 over the length, it's 1 over the length squared, which is the same as the dot product j and j. So let's see. And so that makes it nicer. And you can tweak this a little bit. You could make them a little bit bigger, but you can't make them too big because then you will start seeing some artifacts. So this gives a nice glowy look to it. So now the last thing would be to make these guys twinkle. And for that, we can use, let's use a sine wave. A sine goes from 1 to -1, but I want it to go from 1 to 0. So for that, I multiply by 0.5 and then I add 0.5. And then I need something inside of here. So let's just use iTime first, just to see what we're looking at. So that goes a little bit slow. So let's multiply this. Actually, let's call this t, and then outside of here, if I haven't used it already, I can do float t equals I time times some larger number. Okay, so now obviously they all go in sync, and we don't want that. So what can we do to make them out of sync? Well, we could use the position probably. So let me here, let's say the X position. So let's see. Okay, that doesn't make too much of a difference if I multiply that by some larger number. Yeah, okay, so now you get something that is kind of twinkly. There is some artifact here. I'm not entirely sure where that's coming from. Oh yeah, because across the cell boundaries it's going to be different. Anyways, I'm going to leave it like this for now because this video is already long enough. We can tweak this later to get rid of this. So here, let me actually, if I make this smaller, this can probably be, I mean larger. It's going to be less pronounced, that problem. There you go. So I hope this video was useful. If you liked this or if you learned something, please like, maybe even subscribe so you don't miss when we do the second part of this video. And either way, I will see you next time.